Hello everyone, this is video 13.3 looking at the volumes of solid shapes. So up to this point we've sort of introduced the idea of polyhedra and we've taught a little bit about surface area in a very sort of basic and intuitive way. We'll talk about it a little bit more in this section. We talked about nets as well, which we'll talk about how that sort of relates to surface area. But now we're getting into volumes and calculating the volumes of these shapes. So let's get started. So the first thing we need to do is define what volume is. And so the volume of an object is the amount of space that it takes up, that a three-dimensional object takes up. Now, we can sort of combine this with an idea of capacity, which is how much that object could hold. Now, obviously, if it's a solid object, it can't hold anything because it's solid. But if we were to hollow it out to where the thickness of the walls is negligible, to where it's so thin that it doesn't really change anything between the volume and the capacity, then they're equivalent. The reason why I bring this up is because some of the things we're going to be talking about, students might think about more as capacity than as volume, like a 2-liter bottle holding a 2 liters of liquid. We could also take that object and put it into water. We're going to see this in the next section, and displace 2 liters of volume. So in one regard, we're talking about its capacity. In the other, we're talking about how much space it takes up. Again, we'll talk about this a little bit more in the next section. But whatever way students are thinking about volume is, we want to try to use that as maybe a little bit of a lead-in to as we're talking about capacity. A lot of the things that we talked about in terms of the areas of polygons, like moving and additivity and shearing, a lot of those ideas are still going to apply talking about volumes of solids. And so there's a picture here of some coins that are stacked up. Those are 1-pound coins. And so you can see the first one is sort of a right cylinder. So they're stacked straight up. And the second stack kind of moves to one side and then moves back over. And so moving these coins like this is an example of Cavalieri's principle that we talked about before. You can see that all those coins stay parallel. So we've essentially, on the left cylinder, broken it into those slices, and now we're moving those parallel slices to the left or to the right. You might need to take a second to convince yourself that the cylinder on the left and that sort of like wavy cylinder on the right have the same volume because they're made up of all the same coins. So we're going to need that idea of being able to sort of move that around, as well as thinking about these objects as slices throughout this section. So to find the volume of a prism, there is a general method that we're going to use, and really just one formula that we're going to use for all prisms, and as we're going to see on the next slide, cylinders also, and that is that the volume is equal to the base area times the height. Now, you might be wondering, why is the B a capital and the H a lowercase? And the reason is because the base is an area, so it's a two-dimensional measurement. So if our prism is in centimeters, my base is going to be in centimeters squared. My height is a linear measure, so it's just going to be in centimeters. And so because we're talking about things in two different dimensions, typically we use two different uppercase and lowercase, two different representations of the variables as sort of a reminder that the dimensions don't match. Now the volume is going to be in cubic units. And so if we had, let me make a note of this. So my base area here is going to be, say, in centimeters squared, and my height is going to be in centimeters. So my volume is going to be in something centimeters squared and something else centimeters. And so I'm going to get something in centimeters to the third. So this square and this first are going to make a third power unit here. So you might be wondering, well, if we want different units, or different dimensions of units to be represented differently. How come this is a capital that's a third power and this is a capital for a second power? And the reality of it is we got three different types of units, and we can only have uppercase and lowercase. So yeah, we're kind of using uppercase for anything that's second degree and above. A little confusing, but if we look at the right hand side in kind of in isolation, then hopefully it makes sense, this distinction between the two. We mentioned Cavalari's principle in the previous slide, and again, if we think about these things as slices, then this volume formula should make some degree of sense. So if we think of this rectangular prism as made up of a whole bunch of slices like this, then the volume of that shape is going to be made up of all of those slices. Now, how big are those slices? Well, if we cut them extra super thin, then they're going to be the area um, of that shape. And then how many of them do we have? Well, we have H of them. We have them stacked up H high. Now, the reality of it is that we would need to be slicing these things infinitesimally thin, like to the point that the height of each of those slices is negligible, which doesn't really match with the previous slide because those coins definitely had thickness. So this gets us back to the same place we were at with the area of a circle, where we could look at it with a finite number of pieces of that circle, 8, 16, 32. And then once we start to get into now an infinite number, we start to get into math that's sort of beyond the scope of this class. And the same thing's happening with this rectangular prism. We could do with a class an activity where we were to take a prism and break it into slices. So if this is, say, 8 centimeters high, we could break it into 8 little wedges and then measure the volume of each of those slices and then add those volumes up, which isn't really the same thing because now we're just taking volume and multiplying it by 8 rather than taking areas and multiplying it by height. So there's a little bit of a cheat there. Um, Again, we're kind of limited by the tools that we have to work with at the time. So, as an activity, it sort of illustrates what's going on, even if the math isn't really technically correct. So you have to weigh out whether or not you think building that concept is worth sort of cheating on the rigor of what's really going on. I think there's some merit to it, but you can certainly weigh that out. Um, the other thing that's a little bit of a problem is if we wanted to find the volume of this pentagonal prism, we haven't really talked about how to find the area of this pentagon. We've seen some examples using a geoboard where we could take for certain pentagons, if we have this this geoboard here, we'll do a 5 by 5 real quick, and I'm just going to do the outside pins. And so if I go here to here to here to here to here, now we know that the area of this pentagon is going to be 1, 2, 3, 4 by 1, 2, 3, 4. So it's going to be 16 units squared minus each of these little triangles. And each of these triangles has an area of, well, these are ones, and these are 1.5s. So we could subtract off the 5 and get 11 units squared. So in certain specific cases, if we knew how it fit on a geoboard, we could do it, but that's not a general method. So we haven't really talked about how to do the areas of those too much, and this is sort of a problem with section 2, where it's talked about surface area, but not really. So in a lot of these cases, we would need to be given just what that base area is. The area of this pentagon is this, the area of the hexagon is that. Now, the triangular prism and the rectangular prism, you can certainly do. So if the base shape is one where you know how to find the area, then we can work through the whole calculation. But for something like that pentagon or that hexagon, given what we've covered, given the tools that we have right now, you would just need to be given what that base area is. As I mentioned earlier on the previous slide, for a cylinder, the same idea is going to be true. It's still going to be the base area times the height for the volume. The difference is for a cylinder, this base shape is usually going to be a circle. And I know that the textbook mentioned earlier that it needs to be like a circular shape, so like an oval or like the kidney bean shape would sort of qualify as a cylinder, which I kind of don't like. But typically this is going to be a circle. And so then the base shape we know is going to be pi r squared. So we have a specific formula for cylinders that we can remember, this pi r squared h. I'm sort of the mind, though, that to start off, it's better off if students just see all of these as base area times height, and so that way they'd have one formula to think about, one way to sort of think about what volume is. If I remember these volumes as base area times height, and I can see this mental picture of these slices, then volume makes a little bit more sense. If I just memorize this formula without really any sort of meaning what any of that means, if it's just letters that are going to get replaced by numbers and things to punch on a calculator, then I don't really understand volume as much. There's not really a concept that's tied to it. So ideally, we would introduce this base times height, and then students would arrive at this formula. They would notice that the base area is consistent, and so this formula is consistent, rather than just giving students this pi r squared h formula and having them do it without really understanding what they're doing. So again, building the concept is a crucial idea here, as much as students can with what they have at the time. Speaking of what we have at the time, so we have the volume of a pyramid, and the volume of a pyramid is 1/3 of the volume of the prism with the same base shape and height. And so you can see here this first example, we've got this 1 by 1 square pyramid with a height of 1. And so the height is 1 here. And so we could put it inside this rectangular prism, or in this case a cube, that has this 1 by 1 square base and a height of 1. And so we could find the volume of that prism. So the volume of the prism would be 1 cubic feet, or 1 cubic foot. Yeah, 1 cubic foot. And so the pyramid then is going to be 1/3 of that. Same thing for the second example. We got a 2 by 3, so that's 6 square feet times the height. Here's my height, which is 1 foot. And so that's 6 cubic feet is going to be the volume of the prism. And so now if we take 1/3 of that, then we have the volume of the pyramid is 2 cubic feet. Yeah, I'll let you sort of work through this third and fourth example here. Now, two things to point out. Number one, these are all right pyramids in this diagram. If I were to move this point here anywhere within this top base, then the volume is going to stay consistent. Now, if I start to lean it over and move that point out of that plane, then the volume is going to change. But remember Cavalieri's principle here, as long as I keep everything parallel, then the volume is going to stay consistent. So I could make this an oblique pyramid, and as long as that apex point stays parallel to that base, it stays in that same plane as it is initially, the volume stays the same. The other thing is that 1/3. Where does that 1/3 come from? We're going to talk about that more in class. And we're not really going to be able to do a proof necessarily, at least not a very rigorous proof, but we'll do an activity in class that sort of illustrates and convinces where that 1/3 comes from. So for right now, just know that it's 1/3, and then after class, it'll make a little bit more sense where that 1/3 comes from, or at least how to see the 1/3. As you might imagine, the same relationship with cones and cylinders applies as exists between pyramids and prisms. And so the volume of this cylinder is going to be the base area times the height, so the pi r squared times h. And so the volume of this cone is going to be 1/3 of that. So it's the same idea as if this were a prism and a pyramid. And again, we'll talk about the 1/3 in class. So It's the same. It's the same 1/3. It's the same idea, but where it comes from, we'll talk about more in class. The last one to introduce is this sphere. And we didn't really talk about the surface area of a sphere in section 2. It wasn't really brought up, but the volume of a sphere is mentioned in section 3. If you're curious about the surface area of a sphere, you can certainly look it up. It's 4 pi r squared in case you want to see it. But the volume here of a sphere is 4/3 pi r to the third. Now, if we can't really get too far into the 1/3 right now, we're certainly not going to be able to get into this volume formula too much right now. And so, really this is just sort of a show and tell moment. That's the formula. You need to know it. You need to be able to sort of work with it. Whatever the radius is, in this case, if the radius is 2, then I'm going to put this into the formula, and I'm going to get 4/3 pi r to the third is 4/3 pi 2 to the third. And so that's 4/3 pi times 8, or 32/3 pi is the exact volume here. And if I want to substitute 3.14 for pi and get an approximation, I certainly can. But yeah, this is just a plug and chug formula right now. There's a lot of explanation that can go into it eventually, but it's not going to happen in this class, unfortunately. So the last thing that I want to talk about is the distinction between volume and surface area. So if you think about like wrapping a present, the volume is really what could fit inside that box. It's, we talked about the capacity of the object. Hopefully you're not giving a solid object as a present. Let's maybe like a gold bar. That'd be a nice present. But anyway, so the volume is going to be how much fits inside that box. The surface area is like the wrapping paper on the outside. So that's going to cover up all of the outside. Now, as you might imagine, the larger the volume, the bigger the box, the more wrapping paper you're going to need. At the same time, the more wrapping paper you have, the bigger of a box you can wrap. But as we saw with polygons, we should not expect that the same surface area is always going to give us the same volume, nor should we expect the same volume to be the same surface area. And we saw that with the perimeter and area of polygons. When we kept the perimeter fixed, we had a lot of different surface areas that were possible. And when we kept the surface area fixed, we had a lot of different perimeters that were possible. You might also remember that for a given perimeter, what type of shape had the largest surface area. So you might kind of imagine if we were given a fixed surface area, what shape would have the largest volume. So you probably extrapolate that idea out a little bit. So we'll talk about this a little bit more, but because the calculations get a little bit more complicated, it gets to be a little bit harder to do the same sort of problem for polyhedra that we did with polygons. But we'll look at the idea a little bit here shortly. So for your checkpoint problem, I want you to think about a 4-inch cube. Can you find the volume of that cube? And then can you also find the surface area? Now for the surface area, think about how many faces you have. Think about what shape those faces are. And then can you find the area of each of those faces? Now it's a cube. So if you can find the area of one of those sides, then you just go to multiply it by 6 because they're all the same. And so then that will give you the surface area of that cube. Now, I also want you to consider a 1 by 4 by 16-inch rectangular prism. Now, can you find the volume of that prism? And then can you also find the surface area? Now, the surface area for this prism is a little bit more complicated, so you may want to think about drawing a net of that prism. So the net will allow you to see all 6 of those sides sort of at one time, and then you can find the area of each of those sides. Now, look for patterns in there. Try to save yourself as much work as you can, but then try to find the surface area of that prism. Once you have the volume and surface area of those two prisms, what do you notice that's similar, and what do you notice that's different? This kind of relates back to the previous slide. I don't want to give too much away, But look at what you see as being the same and what you see as being different, and then why do you think that's the case? As always, if you have any questions about this problem or anything else from this section, please bring your questions to class and we'll get them answered. All right, thanks.